What you'll see next is me giving you an example for the Poisson distribution. So we have our y sub i's to follow the mass function, and the parameter here is theta. And obviously what we want to do is we want to be able to come up with theta hat as the estimate using the maximum likelihood estimation technique. Well, the mass function, as you're probably aware, is what I have circled right here. It's e to the negative theta, theta raised to the y sub I, y sub over y sub I factorial. Okay. So what I want to do next, and I'm kind of trying to get you to think a little bit here. What should we do next? Well, hopefully your answer is we'll construct the likelihood function. So given our data y1, y2 up to yn, the likelihood function, because we're dealing with independent and identically distributed random variable, we could take the product of each of the terms. So what we get here is we get e to the negative theta, theta to the y1 over y1 factorial. Same thing in the second part of the product, e to the negative theta, theta to the y sub 2, which is our second piece of data, all the way out to our nth piece of data. Because we're taking the product, we use product notation, so there should be nothing whatsoever for this. I'm going to erase this right here. There should be nothing whatsoever confusing up to here. Now the next thing we do is we're going to take the product, so we're going to simplify this a little bit. The first term here, e to the negative n theta, that's obvious because we have e to the negative theta times e to the negative theta times e to the negative theta n times. So we have e to the negative n theta. The next thing we have is also pretty clear, theta raised to the sum of the y sub i's. Well, we know we have a base, common base, we add the exponents. And the bottom is actually very clear. If we take y1 factorial times y2 factorial times y3 factorial up to yn factorial, then we just have a product of the y sub I factorials. So again, nothing too very crazy just yet, right? So what we would want to do next is I want to take the natural log of the likelihood function. And again, that's going to be the natural log of e to the minus n it's not letting me go up there and write. So it's going to be the natural log of e to the minus n theta times theta to the, let's see, sum of the y sub i's. Just going to over y sub i's factorial. Now, obviously, what we're going to do here is we're going to take the sum of each. So we're going to take, the natural log of e to the minus n plus the natural log of theta sum wise. Doug, pay attention. Minus the natural log, and guys, I've run out of space, but we're just going to put this information right here, okay? Now, guys, it's going to be obvious that the first term we get, wow, look what showed up. All right, so let me go back and make sure where I am here. So the first thing we get, natural log to the e, base e to negative n theta. And you guys, obviously that's going to be negative n theta. And then we're going to have plus, so next thing we have natural log of theta sumwise. So that's obviously going to be pretty easy to do. And then we're dividing the next term, so it's going to be minus, so take the natural log of a product, so we've got the sums of the natural log. What's the right product, right? Product twice by, yes. Okay. Now, that's not sinking in for some reason. So we've got the natural log of e to the negative n theta, which first term has to be right. Second term, we've got sumwise natural log theta, and then the sum of, so yeah, everything looks good there. So guys, what we're going to do next, obviously we want to take the derivative of the natural log of L. With respect to theta. And when we do that, obviously the first term we get minus n. And with respect to theta, we're going to get, see, the derivative of the first times the second. First times the derivative of the second will be the one that we're most interested in. So this is going to just simply give us the sum of the y's divided by theta. So we're going to set this equal to 0. And solve for theta, which results in our estimations. So guys, we're going to have 0 equals minus n plus the sum of our y sub i's over theta. So we get n equals the sum of the y sub i's over theta. So theta hat is going to be equal to the sum of our y sub i's over n. So just as you would think. And then when we think about Poisson, we're thinking about successes and failures, typically coded zeros and ones. So ultimately what we're going to do here, our best estimate will be the sum of our y sub i's. And I don't think we worked with raw data here. So really the result certainly isn't shocking. And just think, you'll get to see this entire video too. So guys, that's the end. Sorry for the confusion. Chris and the gang.